Good afternoon, ladies and gentlemen. Um, Welcome to the lectures of the elementary principles of the chemical processes. As usual, before we go to the new topic, let's recall what we have learned on Monday. This is very important because this will be very likely uh, in your final exam paper. So basically, we want to know the bubble point temperature. Okay, point temperature and the molar fraction in gas phase. So assume we have all the liquids in this box, and then we start. And there are a few species like A, B, C. Of course, you will have molar fraction of the A, B, C, D in the liquid phase, right? Okay, and then we keep the pressure as constant. So once we keep the pressure as constant, we start to increase the temperature. Of course, when we start to increase the temperature, and then eventually we will find a bubble come out, of course, and then a lot of bubbles come out, come out, right? So, and then the first bubble come out at this point, this is what we call bubble point temperature. And we want to determine this temperature. And also, we want to determine the composition of these bubbles in the gas phase. Okay, the composition of A, B, C in this bubble. So you have three informations you want to know. The first one is called TBP, temperature bubble point. And also, YI is the molar fraction of the I species in the gas phase, right? And PI is the partial pressure of the I species in the gas phase. So there are three information you want to know. In the very beginning, the important thing you need to find out the bubble point temperature. Okay? And then you want to find out the molar fraction of ABC, something like this. And then you want to find out partial pressure of ABC. Right. So this is the key. The key is that before you do calculation of how are you going to determine the bubble point temperature, and you have to add up all the partial pressure together. So this is the equation you want to know, is P equal to XA PA star plus XB PB star. Why this happen? Because we understand, we know that this is the equation we want to follow. Okay, according to you, this is why you put Law's law and Dalton's law together, so you can have this equation. And then how are you going to find out? So you know the total pressure, right? Because this is a constant. So you know this value. And you also need this value because this is the molar fraction in liquid phase. So what you don't know is the bubble point temperature and the vapor pressure of A species. So you put it together as a function here. So and then you use try and error. You decide one bubble temperature first, bubble point temperature first, and you do try and error to make this equation become zero. Okay, so try and error to determine TBP. This is called regular Fessy method. Okay, and then because if you think that, well, let's say the bubble point temperature is between 100 Celsius to 80 Celsius, so you start to do try and error between the 80 to 100 Celsius, right? And once you decide 100, and how do you find out the partial pressure of A? Sorry, it's not partial pressure. This is the vapor pressure, okay, of A pure species. So use Anton equation, right? Use Anton equation. Okay, you put the ABC as a constant, and you get this answer. You get this number value, and then you get this value, you put it here, and then to try to make this equation become zero. And then so you obtain the bubble point temperature. Right. So once you get the bubble point temperature, according to Lao's law, the partial pressure is equal to XAI PI star. So because you know the bubble point temperature, right? So you will know the vapor pressure of A species, and you already know the molar fraction in the liquid phase. So you will obtain partial pressure of ABC. And once you know the partial pressure of ABC, according to Dalton's law, you know the molar fraction of the A species, B species, C species in the gas phase. So this is how you get the answer of these three: temperature, bubble point temperature, um, partial pressure of I species, and molar fraction of I species. Okay, so bubble point temperature. And how are you going to get bubble point pressure? Again, there are three things you want to know, you want to find out, right? It is, again, in this liquid box, this box full of all the liquids. And again, you have A species, B species, and C species. And then at this time, you keep the temperature as a constant because you want to find out the bubble point pressure. So you keep the temperature as a constant. And then you decrease the pressure. You decrease the pressure. And then you will find bubble come out. At this point, the pressure is called bubble point pressure. And how are you going to find out bubble point pressure and the molar fraction of I, Yi, and the partial pressure of I species? Again, I hope you still remember I told you that you make this all together, the total pressure is equal to this equation. And once you know the temperature here, because this is the constant. So if you know the constant temperature, then what you need to know is to find out the vapor pressure of A species, vapor pressure of B species, according to what? According to Anthony's equation. Anthony's equation tells us that as long as you know the temperature, you put it here, and you get ABC, and you get the partial pressure. You got the vapor pressure of A species. Okay, so this is very straightforward to get the bubble point pressure. Okay, and then you can achieve the bubble point pressure. So once you achieve the bubble point pressure, and how are you going to get the molar fraction? Lao's law, right? Lao's law. Okay, so you know this, and you know this. Of course, you know this. And then how are you going to get the partial pressure? Dalton's law. So this is Lao's law, and this is Dalton's law. Okay, so you are playing Dalton's law and Henry's law all the time. Sorry, Dalton's law and Lao's law and Dalton's law, right? Okay, so the third situation is to find out the dew point temperature. Dew point temperature is that there are two information you want to know: the dew point temperature and the molar fraction I species. You might say, well, where's the partial pressure? There's no partial pressure, right? Why? Because we want to find out the molar fraction in liquid phase. Of course, in liquid phase, you don't have pressure. Right, so in this box is full of all the gases. And then you have A species, B species, and C species. And of course, you understand you will have molar fraction A of the A, B, C species. Okay, and then because you want to know the dew point temperature, so you keep the pressure as a constant. So you know the pressure, total pressure, and then you start to decrease the temperature. You decrease the temperature, and you'll find out the first droplet of the liquid will come out. And at this moment, you want to find out what is the temperature, and also you want to find out the molar fraction of A species, B species, and the C species. Okay, so how can we find out the temperature, dew point temperature? Again, use try and error according to this equation. So once you want to find out dew point, either temperature or pressure, this is the equation you need to remember. I don't tell you this in your final exam. You need to remember this because this is Lao's law. Okay, XA, XB, XC, XD together, all the molar fraction get together will become 1. And molar fraction will be equal to this according to Lao's law. Right? Okay. And then you make this equation equal to 0. So you play around with the temperature. Again, if I told you the dew point temperature is between 60 to 80, so you start to put the 60 and 80 into this 60 and 80 temperature Celsius into this place, and you find out the vapor pressure of A, vapor pressure of B, and to make it become 0. So again, you use trial and error method. And then you should use Anton equation, right? To put it here and try and error to get the dew point temperature. Okay, so once you get this, then how are you going to get the molar fraction of Xi? Here, right? Dalton's law. So because you know the total pressure as a constant, right? And now you know this is initial condition. Okay, molar fraction initial condition. All you don't know is you already tried you use try and error to get this number, right? And then you can get XA here according to Lao's law. Okay. So dew point pressure, again, if we have species in the gas phase, and we know the molar fraction in the gas phase, and then we keep the temperature as constant because we want to find out dew point pressure. So, and then how can we get the dew point? Increase the temperature or increase the pressure or decrease the pressure? Increase, right? Increase the pressure. So you'll get bubble come out. You will get the droplet come out. The first droplet, and again, you want to find out what is the dew point pressure here, and you want to find out the molar fraction of this droplet. Okay, follow the same equation. The molar fraction in the liquid space, in the liquid phase, get together equal to 1. And you try to modify this equation according to Lao's law. And then once you know this, and because you already know the temperature here, so you don't need to use trial and error to get the dew point pressure. Why? Because the temperature is constant. So you put the temperature in here, and then you get this answer according to Anton equation, right? Okay, and what you don't know is total pressure. Okay, and this is what you know because this is the molar fraction in the gas phase. So all you don't know is this one. This is unknown. So you take this out and make this become 1. So in the end, you will get this answer. So the key is that temperature here constant, and then use Anton equation to find out this, and you get the total pressure. Okay, so once you get the total pressure, you use Lao's law to get the Xi, which is the molar fraction in the liquid phase. Right, so that's it. So what I want to remind you is that in your final exam, I might ask you find out the bubble point temperature, or find out bubble point pressure, or find out dew point temperature, or find out dew point pressure. And then you need to go home and practice this example. Okay? And then on Monday, we also talk about the graphic representation, right? Remember this? This is represent the temperature. If you keep the pressure as a constant, and this is you keep the temperature as a constant, and you play the bubble point pressure with the molar fraction. Okay. And then this is an example I want you to practice at home, because actually this is the question of the Kahoot today. So the Kahoot today is that the graphic representation. Okay, graphical representation of the liquid vapor equilibrium. So I want you to know that I already show you how to find out the bubble point or dew point temperature or pressure, especially bubble point temperature and the dew point temperature, right? Okay, so I don't want to waste your time here today. but I want to tell you that this is the question of the Kahoot today. Okay. Right. So for the summary of this binary system, this is incapable for the non-ideal solutions. This is for ideal solution only. Okay, this graph is for ideal solution only, and also this graph is not suitable for the systems immiscible or partially immiscible liquid. For example, water and MIBK is not 100% miscible, right? It's partially immiscible. So you cannot use this graph for this binary system. And the system we gave you, the example we gave you is that benzene and toluene, right? Okay. Right. So in the end, is that for the section 6.3 and section 6.4 is that we mainly talk about the single component for the gas liquid system. You have gas and liquid system, and you have species in gas and liquid. For the single component, we start to know the single component. You use water as an example. Okay, and then for the multi-component, only one condensable component. So this system is only A, B, C, D, and only one condensable, which is water, right? Only one condensable. This is the second case. The third case is that multi-component liquid systems, which maybe have more than one condensable component, like water and the sulfur dioxide, right? So this is two condensable. So, and then finally, we talk about the two component systems. So we use benzene and toluene as an example. So for a single component, what we learn is, firstly, we learn Kraepelin equation. Remember, the Kraepelin equation tells us what? Find out latent heat. Find out latent heat. Okay, how do you find out latent heat? I already told you, right? And the second is that we learn the Clauser's Kraepelin equation. Clauser's Kraepelin equation is that once we find out latent heat and we find out the constant B, we can use this equation to know the pressure, the vapor pressure related to what? To temperature. So if you find out if you have a latent heat and a constant B, you can use this equation to get the relationship between the vapor pressure and temperature. Okay. And Anton equation, this is an empirical equation. We use this a lot in the section 6.3 to 6.4. Okay. And then we also introduce you the Koch chart. The Koch chart is again related to the temperature and pressure. Right. So section 6.3, we mainly talk about the multi-component, one condensable component, right? One condensable component. We start to introduce you Laws law. Okay. And do you remember you learn superheated vapor? Remember superheated vapor? This is that there's no water, there's no liquid exist, only vapor. And we can increase the temperature to make the vapor very, very hot. So the vapor pressure is never reached to the saturated vapor pressure, right? So this is what we call superheated vapor. So you can increase the energy a lot. You can increase the energy of water vapor a lot. Okay, it can go to 300, 400. And we use an example of turbine, right? Turbine or power generator or power station. And then we introduce you the dew point. Right. So for the multi-component gas liquid system is the Laws law and then Henry's law. Right? Okay. So, and we also tell you the ideal solution. So in this case, if I have 1, 2, 3, 4, if I have 4 species, could you please tell me which 2 are applied for Laws law? Which 2 are applied for Henry's law? Can you tell me? Nobody want to get points? 0.5? Yes, please. Thank you. That's correct. Very good. So this is for solvent. Solvent normally is applied for Laws law, but this is not easy to condense. We use Henry's law. Okay, and if this to apply system applied to Laws law and Henry's law, we call this ideal solution. Okay, and then remember that in the end we talk about dew point and bubble point calculations. That's what I just introduced. I just recapped that to you, right? Okay, and then we have, if we have, this is simple case which is a two-component system. We use Benjamin to learn as example, TXY and PXY diagrams. And you need to know how to read the diagrams in order to find out dew point and bubble point temperature and dew point and bubble point pressure. Okay? Right. So we finished the section 6.4. Right. Next topic is the solid solution in solid and is the solution of the solid in liquids. What is this? What is this? That means that in the section 6.4 we are talking about liquid and gas, and now we want to know solid and liquid. Okay. The first of all, of course, is solubility and the saturation. So solubility is what? If you have a teaspoon of a salt, and then you put a teaspoon of salt into this water, and if you keep on putting the salt into the water, salt will dissolve, right? But eventually you will saturate it, so there's no more salt can be dissolved because it reached the maximum of the solubility. Okay, so the solubility of a solution, a solid in a liquid, is the maximum amount of that substance that can be dissolved in a specified amount of the liquid at equilibrium. So the solubility of ionic compound in water is that if you put a salt like NaCl, NaCl will dissociate, become sodium cation and chlorine anion, right? Right. So which rise because the attraction between the positive and negative charge. So for example, if this is silver chloride dissolved in the water becomes silver cation and the chlorine anion, right? So, and that is that the silver, when the positive charge will close to the negative charge of the water, which is negative charge is oxygen, right? So this one will be closer. So the water take the sodium silver chloride apart. Okay, and of course the chlorine anion will attract the proton, the hydrogen, right? So this is what we know, that if you put the sodium chloride into the water, and then this is sodium chloride, right? And the anion anion will be taken away by the proton, the hydrogen, right? And the cation, which is the sodium, will take away from the oxygen. Okay. So this is what we find out, and this is what we call hydrated ions. Hydrated ions. Right. So in a section 6.4, we are dealing with the liquid and the gas. So if we put a tape, for example, if we put a teaspoon of the sodium chloride into the water, will it affect the vapor in the gas, the water vapor in the gas phase? Will it affect that? The answer is yes. Okay, so and then it depends on how many salts into this water. Okay, so actually the solubility is a function of species, like sodium chloride, silver chloride. It depends, right? So it depends on, it's a function of species, and it's a function of temperature. is a function of pressure. So the temperature change, solubility change, pressure change, solubility change. Okay. So for the condensed phases, the pressure dependence of the solubility is typically weak and usually neglected in practice. So basically, solubility is the function of these three factors, but pressure is not that strong factor. So normally we regard the pressure. So the solubility becomes the function of the species and also the temperature. Okay, so let's talk about the species and temperature. What's related to that? So for the species, we give you an example. Species have a solute and solvent. Solvent, let's say, for example, water, and solute will be some species. For example, 100 grams of water at 20 Celsius, this temperature is fixed, right? So you have 100 grams of the solvent is fixed. So this condition can dissolve 222 grams of the silver nitride. It's very big. 100 grams can dissolve 222 grams. Okay, this is a lot, but the 100 grams of water can only dissolve 0.003 grams of the silver carbonate. Okay, and also then this is much less. 100 grams of water can dissolve only 0.00002 grams of the silver bromine. Okay, so it depends on the species. If you have different species, you have different solubility, of course. And how about the function of the temperature? You understand, right? If you have a higher temperature, you have higher solubility. This is an example of the silver nitride. At 20 Celsius, we understand there are 222 grams of the silver nitride can be dissolved. How about 100 Celsius? If I increase the temperature, the solubility will be high, right? In this case, it's 952 grams. So you increase the temperature, you increase the solubility. And the other term is called saturation. So why saturation? The solution that contains as much as the dissolved species as it can at equilibrium is said to be saturated, right? So if you keep on putting the sugar and salt into the water, eventually you will get saturated. So there's no more. The water can eat no more sugar or salt, right? So the solution in equilibrium with the solid solution must be saturated with that solute. If it were not, most solute will be dissolved. That's of course. Right. And here, this is the term called supersaturation. What is supersaturation? The supersaturation is that, this is saturated, and then supersaturated condition. So if a saturated solution is cooled and solubility of the solute gradually decrease, in order for cooled solution to turn to equilibrium, some solution must come out solution as a solid crystal. So for example, this is saturated solution at, let's say, 60 Celsius. And if I decrease the temperature, and then because if I decrease the temperature, the solubility will be decreased, right? So some of the solid will come out. So it depends on the speed of the decreasing the temperature and also the speed of the solid come out. Which one is faster? If the decrease of temperature is faster, then the solubility, then the solid crystal cannot be formed that fast. At this moment, we call this situation is supersaturation. So the crystallization rate may be slow. Okay, the crystallization rate is slow. However, so that the metal stable condition can be exist. So this is called metal stable. It's not stable, but it's between stable and non-stable. We call metastable. So the condition can be exist in which the concentration of the solute is higher than the equilibrium value at the solution temperature. Under such condition, the solution is said to be supersaturated. So if you, for example, this saturated solution is at 60 Celsius and I decrease to 40, and you don't see any crystal come out, then we will say this condition is a metastable condition, and this is a supersaturation situation. Okay, so the solution is said to be supersaturated. And when something come out, you'll see the crystal come out very, very fast because this is supersaturated. So once you have a seed drop into this supersaturated solution, the crystal will come out immediately. Okay, so the differences between the actual and the equilibrium concentration is referred as a supersaturation. So I have a video for you here. So assume, let's think that please, this is supersaturated, and I put a seed into this solution, the crystal will come out immediately. Okay. So what we use this for? As you know that you can create crystal using saturated solution. So there are many type of crystal was formed by this kind of solution. Okay, supersaturated solution. This is one of example. Is KH2PO4, and this is a very important crystal for laser. Okay, material for laser. So if you control the temperature and speed well, you can make single crystal. Okay, in a video that's called polycrystal. And if you want to make single crystal, you need to control the crystallization rate very well, so you can make a very beautiful crystal like this. Okay, another supersaturated is the carbonated water. You know, you have sparkling water, right? Sparkling water, if you open the cap of the bottle, and then the bubble will come out. Okay, we call sparkling water. So carbonate, you put the carbon dioxide into the water using high pressure. Okay, it's a saturated solution of the carbon dioxide gas in water. So you feel well if you drink this, right? So at elevated pressure in the bottle, the more carbon dioxide can dissolve in water than the atmospheric pressure. Okay, so the atmospheric pressure, the carbon dioxide gas escapes very slowly from the saturated liquid. Okay, so this process may be accelerated by the presence of the neutralization site with the solution, such as the small bubbles. I just show you, right? Okay. Right, so this is the example of the crystallization and filtration. I think I will introduce this quick because we don't anyway. Okay, so the saturated aqueous means what? Aqueous means H2O, right? Okay, solution which is silver nitride at 100 Celsius. So you have water and with silver nitride, and you want to take the silver nitride away from the water and make the silver nitride become a solid. So what you need to do is crystallization and filtration. We learned crystallization and filtration well already. Okay, so crystallization, you decrease the temperature from 100 to 20. Of course, the solubility will decrease. If the solubility decreases, the sum of the most of the silver nitride will crystallize, and you can get the crystallized silver nitride, right? So you decrease to from 100 to 20, and you feed the 150 kilograms per hour, for example, of this solution into this process, and then you come up with what? Saturated solution together with what? Solid. So you have solid silver nitride, and you have liquid silver nitride. Okay, so at 20 Celsius, you still have solid. You have solid as well as liquid, right? Water together with saturated silver nitride at 20 Celsius. So you need to have a specification. You need to know the solubility of the silver nitride in water at 100 Celsius. And also you need to know the solubility of the silver nitride in water at 20 Celsius. Okay? And then you need to know a filter. And after that, because you have solid and liquid, so you need to separate these two. So you have rotary, remember this? Rotary vacuum drum filter. you can filter that. You can get a cake which is filtrate. Filtrate is that you got a solution, right? The solution is this one. Okay, silver nitride saturated in water at 20 Celsius. Okay, and then you have wet filter cake. Wet filter cake, you have two things. The first is solid, second is liquid. So 80% is solid crystal, and 20% is saturated solution. The saturated solution is what? Is you have solid and liquid, right? Okay, we already introduced this kind of topic to you before, so I hope you understand. So and then we dry this. We take the filter cake out, and we dry it, and we get the water vapor, which is 100% water, and we got a solid. So this is the process. So all we need to know in this condition is solubility of the silver nitride at 20 Celsius and also at 100 Celsius. Okay? And of course, if you know this, you know the fraction. So if you know the fraction, you can put these things here, right? Okay, if you know the fraction of the 100 Celsius, this is 100 Celsius. So the fraction is 0.9, and of course, water will be 0.095. Okay, the same as this, right? Sorry, if this is 20, right? 20 is here. 20 Celsius, the solubility is the molar fraction of the water. Sorry, the molar fraction of the silver nitride is 0.689. So you will have this 0.689. And also this one is what? 31.1. Because these two get together will be 1, right? Okay, and then this is 20 Celsius. This is 100 Celsius. And how about this one? 120 Celsius. So you get the same number here. Of course, you get the same number here. Right, so you don't know is you put the unknown here. Mx is silver nitride, My is liquid, right? Liquid is 2. And then M1, M2, M3. I think, right. So I don't read the text with you together. I think we already go through this process with you before. And the important information you want to know is the solubility of this. And you use the solubility according to this table and put the number, molar fraction in each streams. And that will be okay. Right. Okay. So next topic is called hydrate salt. Hydrate salt. Right. So this topic is talking about hydrated salt. Hydrated salt. What is hydrated salt? And what's hydrated salt related to solubility? Right. So if we have two component system, we talk about the solid and liquid, right? And then this is the example. And then we put the solid things here, and we want to know the solubility in the liquid. Right, so I will skip this soon. So you know that in order to notice the Gibbs phase rule is 2, and this 2 phase, right? This is 2 and 2. So we need temperature and pressure. Okay, we need temperature and pressure. So this is the solubility of the inorganic solutes. So I hope you still remember that the y-axis, the x-axis is temperature, y-axis is solubility. I hope you remember that I told you if we increase the temperature, the solubility will increase. Why? Because its energy is increased, right? Energy increase is easier to tear pull the crystal apart, okay, to become ions or to become molecules. Okay, so because the property of liquid and solid are only slightly affected by the pressure, the single plot of the solubility versus temperature may be applied over a wide pressure range. So we don't talk about pressure already. I hope you still remember. The solubility is the function of the species, temperature, and pressure. But pressure, we regardless the pressure because it's just a minor factor only. So we mainly dealing with the species and temperature. Okay, so this plot tells you that if I increase the temperature, the sodium chloride increase, the solubility increase. Of course, you can see that is slightly increased, not heavy, not heavily, right? How about the potassium nitrate? The potassium nitrate increases very fast, okay, by a factor of 10, okay, increase very fast. However, there is one exception. This exception is the sodium sulfide. Okay, the sodium sulfide is that the temperature increase, the solubility increase, but unfortunately at 40 Celsius, the solubility decrease. This is abnormal. This is abnormal. Why this is abnormal? I'm going to tell you very soon, because this is called hydrated salt at 40. The sodium sulfide start to eat water, become another compound. And this compound we call hydrated salt. Hydrated salt. So this is another example of the solubility of the organic solute. Okay, you can see that some of them, as you can see, the temperature increase, normally the solubility increase, but there are some abnormal, some exception cases. Right, and then this case, I just want to tell you that this is potassium nitrate. I don't want to waste your, I think the potassium nitrate, I will skip this example. Right, so the hydrated salt is like this. This is cobalt chloride. And if this one, without water, this is blue. But with water, it becomes red. And why it's still solid? It's not liquid. Why? Because, you know, this water molecule go into the crystal. Water molecule go into the crystal. And the color change. So this is what we use silica gel. You know, when you have dry silica gel, it looks like blue. And when it's too humid, for example, this RH is 20, RH is 50, become red. I hope you still remember what is RH. Does anybody want to tell me what is RH stand for? What does RH stand for? Tell me. 含水量，0.3分好了，好不好？好，真正的 R 是什么 ？H 是什么？相对湿度 ，Thank you。Relative humidity， 相对湿度 ，right？ So 如果你在家里有温度计跟湿度计的话，你会看到一个东西叫 RH。RH between 40 to 60 is a very nice condition to stay. If the RH reaches to 80, it's too humid. You don't feel well. If RH is 20, it's too dry. You don't feel well too, either, right? Okay, so this is the kind of chemical you can use to detect the humidity, or you can put these kind of things in the dry box, and if this silica gel get wet, it change the color, and you know you need to change, you need to refresh, or you need to change the condition. You need to make the box drier. Okay, so when a certain solution crystallizes from the aqueous solution, the crystals are hydrated salt containing water molecules bonded to the solute molecules. So this is what we call hydrated salt. Right. So hydrated salt is the number of the water molecule associated with each solute molecules vary with the crystallization temperature. Okay, so this is one of the example. Just want to tell you that, you know, if we increase, for example, this magnesium sulfide is that with the six water into this crystal, and this temperature is 48 to 67. Okay, and then if I increase the temperature, of course you will have the water inside this crystal will become less. This is the case. Of course, if you increase the temperature, if you decrease the temperature, the water in the crystal will be more. So this depends on different temperature. You will have different water inside this crystal. Okay, so the hydrated salt is also related to the content of the water in the hydrated salt is also related to the temperature in this case. Right, so the solubility and water of the hydrate is that, the sodium sulfate is below 40, there's no water. So it's, the solubility of the sodium sulfate in water is increased with the temperature. However, above 640, the sodium sulfate start to have 10 water molecules inside this crystal. So the solubility doesn't increase. Why? Because water goes into the crystal. So this crystal doesn't become ions, right? Sodium ion and sulfate ions. So the solubility won't go up, right? So the change from the anhydrous to the hydrated form, the solid at 40, is responsible for the discontinuity in the solubility figure. Okay, here. Right. So this is the example of the production of the hydrated salt. Again, I don't read the text with you. I just want to tell you that how to do the mass balance using with the hydrated salt. Okay, so aqueous magnesium sulfate solution is 104 Celsius. Again, you have liquid. This is saturated, right? This is saturated. So you need to know the solubility of the magnesium sulfate at 104 Celsius. Okay, and we already told you that here is 31%, 31 weight percent, and 69 weight percent, and this solution will be fed into the crystallizer. And of course, the temperature dropped from 104 Celsius to 10 Celsius. And obviously, you understand the crystal will come out from the solution because the solubility of this crystal is lower, right? The solubility of this at 10 Celsius is lower than the solubility at 104 Celsius. And then you have two streams come out. One is crystal. One is the crystal. The foam is, at 10 Celsius, the magnesium sulfate has 7 waters per 1 molecules. Okay. And then when it come out with that saturated solution at 10 Celsius. So saturated solution, you have 32.2 weight percent magnesium sulfate in water, right? And the rest of them is water. Okay. And then you want to produce 1 ton per hour of the magnesium sulfate. I should say hydrated salt, hydrated magnesium sulfate. And the important thing is that you want to find out what is unknown here. It's M1, M2. Okay, so you have 2 unknowns, and you have 2 equations. You have 2 species, right? 2 species, magnesium sulfate and water. But the problem here is that this is water and magnesium sulfate. So for the mass balance, you don't use this hydrated salt for the mass balance. You should use this as a mass balance. So the key for this example, that's the reason I want to talk about this example with you, is that remember you do the MgSO2 balance. You don't do MgSO4 with 7 H2O to do the input equal to output. Okay, so you have water input equal to 2 output, and magnesium sulfate input equal to 2 output. That's why you need to know. Okay, so I don't go to detail with you. Please practice this by yourself. Right, ladies and gentlemen, this is a very interesting topic, which is called colligative solution property. What is colligative solution property? You know, when you eat ice cream, you know, the ice cream, inside ice cream there's water. And then you understand the ice cream, the temperature of the ice cream is less than 0 Celsius. So why the water doesn't become ice? The water is still liquid. Why? This is because you put the sugar, you put the protein into this water. That's why the melting point is not 0 Celsius. Okay, so this is what we call colligative solution properties. So what is colligative solution properties? Again, if we think of the liquid and gas phase, we already know this situation already. And here, we know that we want to play around the temperature and pressure, right? Temperature and pressure. And then if we fix the pressure and we want to know the temperature, and we also want to know the unknowns in gas phase and unknowns in the liquid phase. And now the interesting thing is that if I put solid, this is liquid and this is gas, right? If I put a solid material into this solution, for example, I put a salt or I put a sugar into this solution, and what happened? Will it affect this number or not? Well, of course, it will change this number, right, because of the molar fraction. Will it affect this? Will it affect the partial pressure or not? And this is what we know about the colligative solution property. Okay, so what is colligative solution property? The physical property of a solution and the pure solvent are different because you put something into this solution. So, for example, you put the water, you put the salt, or you put the sugar into this solution. So, colligative properties are properties of the solution that depends on the numbers of molecules in a given value of the solvent and not the properties identity, so like size or mass. It's just the number, okay, of the molecules. I'm going to tell you this later. So if you change the amount of this, if you change the amount of salt or sugar into this solution and something changed, like melting point or boiling point. So what are these changed? The physical property change of what? Basically, they change of 4 things. Here, we just introduce you 3. Vapor pressure. So the pressure will change. This salt will change the water vapor pressure here. Okay? And then you will change the boiling point. Boiling point of the water or boiling point of the solvent. And also you will change the freezing point, which is melting point, right? Or boiling point or melting point, we call freezing point. So how are they going to change? So how are they going to change? The colligative property includes what? You will lower the vapor pressure. Why? Imagine if you have a salt in the water, and the water want to come out. Water want to vaporize. And then the salt will what? They'll grab it. Say, please don't go to vapor phase. Okay? So the vapor pressure will be what? Will be lower. The more sugar you put into this solvent, the lower vapor pressure you will have. So the more concentration of the sugar or salt into this solvent, you will have a lower vapor pressure. So you change the gas phase. And also, you will evaluate elevation of the boiling point. You will increase the boiling point. Why? For example, if you have 100, water is 100 Celsius, right? Boiling point of water is 100 Celsius. If you put the sugar in or salt in, the boiling point will increase. And then what? The freezing point, the melting point will decrease. Why? You might imagine that sugar or salt grab the water molecules very well. So it doesn't want the water vaporize or water become ice. Okay. And the last one is called osmotic pressure. Okay, this is not concerned in this text, so we don't discuss about this. So what we need to know is the top three. So the qualitative, and also as I told you that the colligative property is the function of species and concentration. I just told you that if you have more concentration, the vapor pressure will drop badly, right? The more you have, the lower vapor pressure you will have. Okay, so this related to species as concentration is also the function of the species. So for the species, for a concentrated solute, okay. So let's think of the colligative property first is the vapor pressure. So this cartoon shows you that this is water molecule, right? And I hope you remember that the water molecule here, and if you have a sodium cation, the sodium cation will attach to what? Oxygen, because Coulombic attraction, right? Because this negative and this is positive, this is negative. Oxygen is negative, right? And chlorine anion will close to proton, which is the hydrogen, right? Hydrogen plus. So it seems that there's kind of interaction and energy, bonding energy together. So you don't want the water go up. So of course, according to these two figures, you will understand if there's no salt, the water vapor, the water is easy to jump from the liquid to a gas. There are more molecules in the gas phase. That's why the vapor pressure is high. And this one grab the sodium and chlorine, grab the water molecules, then they come out. So the vapor pressure will be low, right? Low. So the vapor pressure of the solvent is a proportion to its molar fraction. So if I have more salt into the water, the vapor pressure or the vapor will be much less, and the vapor pressure will be lower, right? Okay, so that's the difference between the vapor pressure, pure water and the seawater. If you have seawater, the vapor pressure will be what? Will be lower than the pure water, right? Right. And the concentration increase, vapor pressure decrease. Okay. And this is kind of a very interesting experiment. So when a beaker containing seawater is placed to a sealed container with the beakers of the distilled water. So this is the pure water. This is seawater, and you have a container which is a closed system into these two. And then when slightly higher vapor pressure of the distilled water lead to the net transfer of water from the beakers of the distilled water to the beakers containing seawater. So when time goes by, you will see the pure water. This container has less water. This container, which has the seawater, will be more. Why? Because they have different amount of vapor pressure. Sorry, they have different vapor pressure. So the amount of the water will decrease in the pure water. The amount of water in the seawater container will increase. Okay. Right. So, and when we talk about the vapor pressure, then how about the melting point? When the freezing point of the pure water is 0, but the melting point can be depressed by adding the solvent, such as the salt. So if we put a salt into the water, the melting point will what? Will decrease, will depress, right? Okay. So for example, this is an example of water. For example, the solvent 100%, there's no salt. The melting point will be what? Will be 0, right? Okay. However, if you put salt into the water, the melting point will be what? Depressed. It becomes minus. Okay, and then if you have more salt into the water, the melting point will be further decreased. You don't need to remember this number, but you need to know if I increase the more salt, that will be decreased. Why? Because I don't want it to become solid. I don't want water molecule to become vapor, because they have very strong interaction between salt and the water. Okay, that's why any fluorine substance added to the water will cause freezing point dropped. Freezing point drop, right? Sugar, alcohol, any chemical salt will lower the freezing point and melt ice. So it's used to road, right? So this is one of the things, in the winter, if in Taiwan we don't have this chance to see that, but if you United States, in Japan, you will see a lot of snow, and you don't want snow to go in, occupy the road, right? You still want your traffic go smooth, so you put the salt into on the road, right? So the melting point will drop. Okay, so you don't see the ice on the road. Okay, of course you don't put sugar, right? Nobody put sugar. You put salt. Okay, and the coolant, if you have your car or your motorbike, and if you go to a very cold place, then coolant is liquid, right? If the coolant liquid and the temperature drops to 0 Celsius, the liquid becomes solid. Your car is gone, right? Okay, so you put the chemicals into that, so you don't have a chance. And also some of the plants, you have sugar inside these plants. Of course, sugar with water. So this kind of plant doesn't become ice, when temperature reaches to 0 Celsius. And also you make nice food, okay, protein into the water. You ice cream, right? So you make nice dessert. You can use it. You can have this below 0 Celsius. This is what we call colligative properties. Okay, so so this is how we do the separation of seawater, and that I just think we just run out of our time today. So next Monday is the holiday, right? So we will have lecture on Wednesday, and on Wednesday we will talk about colligative property calculation. When we increase the concentration of the salt, the melting point dropped, and we want to know concentration related to the temperature, the temperature dropped. Okay, so we need to do some calculations. Okay, so that's it for today.